what do we mean by amines? Tell me. What are amines? Ammonia. Organic derivatives. Organic derivatives of ammonia. Okay then. Nitrogen containing compounds. Nitrogen containing compounds. Okay. So we'll start with the amines. We'll start with the amines. So what do we mean by amines? Tell me. What are amines? Ammonia. Organic derivatives. Organic derivatives of ammonia. Organic derivatives of ammonia. Organic derivatives of ammonia. Now this is your ammonia. Yes. There is a lone pair of electron. We know that the hybridization of this nitrogen is sp3 and the shape is pyramidal. The shape is pyramidal. Geometry is tetrahedral. Okay. Now if I replace this H with R group, alkyl group, so this is your amine and this is your 1 degree amine. Okay, 1 degree amine. Now suppose the other H is also replaced by the alkyl group. This is your 2 degree amine. And then we have something like this, which is your 3 degree amine, tertiary amine. Yes or no?
Yes, sir.
Yes? So these are your organic derivatives of ammonia. Tell me this is clear.
Yes, sir.
Yeah? Okay.
Yes, sir.
Now how to write the nomenclature, IUPAC nomenclature. So we are discussing the aliphatic amines first. So suppose if I have this, what is the name of this?
Methanamine.
Is this your 1 degree amine? So methanamine. Alkanamines is basically the name. So methanamine. Perfect. What about this? Propanamine or propan-1-amine? Propanamine. Or we can write propan-1-amine. Yes or no?
Yes.
Yes?
Yes.
And suppose if I have this CH3CH NH2. First of all, tell me, is this your 1 degree, 2 degree or 3 degree amine? This is the 1 degree amine. What is the name? Propan-2-amine. 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 Is that clear?
Yes, sir.
Yes, sir.
Alright. What if I have this CH3, NH, CH2, CH2, CH3? First of all, tell me, is this your 1 degree, 2 degree or 3 degree amine? 2 degree amine. Very good. Now the bigger alkyl group makes alkanamine. Okay? So this bigger alkyl group, makes alkanamine. Clear? So what is the name? See, N-methyl propanamide. Propanamide. Yes or no?
Yes, sir.
Yes, sir.
Those who are present online, tell me if this is clear.
Yes, sir.
Propanamide. And what is this? Is this a 3-degree amide? What is the name? So the bigger alkyl group forms alkanamide. So it will be glutenamide. So this is your N-ethyl alphabetical order. N-ethyl, N-methyl, glutenamide. Yes or no?
Yes, sir.
Glutenamide. Tell me if this is clear.
Yes.
Yes, sir.
N-ethyl, N-methyl, glutenamide. Is that clear to everyone?
Yes.
Yes, sir.
Alright.
Yes, sir.
Shall I?
Yes.
Let us discuss the structure. Let us discuss the structure. You know, it is a pyramidal in shape. And like I said, the hybridization of this nitrogen is sp3. Obviously, there will be lone pair, bond pair repulsion. Because of that, the bond angle is less than the usual tetrahedral angle of 109.5 degrees. Yes or no? Okay. Now, suppose if I have this. Suppose if I have this. Please tell me, is this nitrogen chiral? Chiral? What is the hybridization? sp3. sp3, right? Yes or no?
Yes, sir.
Okay. Now what I am doing, I am rotating it. See, you know that it is a normal tetrahedral. Just one of the bond in that usual tetrahedral, for example, CH4, is being one of the CH bond is basically replaced by this lone pair. Now what will happen? Suppose if I rotate this by 180 degrees. Suppose if I rotate it by 180 degrees, which is your C2 rotation. Suppose if I perform the C2 rotation, 180 degrees.
Yes.
Now what will happen? Look here. Can you please give me the pens? I have the pens. One. Look. This is the lone pair. This is the argon group which is in the plane. One is behind and one is in front. What I am saying, I am rotating it by 180. If I rotate it by 180, can I say this one will come this side? And the one which is in the back will come in the front. Yes or no?
Yes.
Yes or no? So this is what I am doing. So when I am rotating it by 180 degree, what is happening is N. This is your lone pair of electrons. This becomes your R3. Yes or no? The one which was at the back comes in the front. So this one is your R1 and this is your R2. Any problem?
Yes.
No. Now what I am doing is, I am passing the plane over here. And I just want to see the mirror image of this. So if I want to see, I want to look at the reflection. Okay, plane of reflection. Now look here, this R3 obviously will get its image somewhat here. And the one which is in the front will still be in the front. And the one which is in the back will still be in the back. Yes or no? So can I say I will have something of this sort? And don't pay will hold it down. This one will be your R3. And the one which was in the front is still in the front. And the one which was in the back is still in the back. This is your, tell me, R1, and this is your R2. Tell me this is clear.
Yes, sir.
Yes? Tell me this. Now, can I say that suppose if this is A and this is B and this is B, then A and B are your non-superimposable mirror images of each other? Yes or no? They are your non-superimposable mirror images of each other. So can I say they are enantiomers? They are enantiomers? Okay. Non-superimposable mirror images. Now, look here. You know what happens? So they are enantiomeric forms. Yes, they are your enantiomeric forms.
Yes, sir.
So can I say that this amine A should be optically active? Can I say this should be optically active?
Yes, sir.
But in spite of being chiral, it is optically inactive. In spite of being chiral, it is optically inactive. It is optically inactive. Why? Why? My question is why? And the answer lies in the pyramidal inversion, what we also call umbrella effect. So this is your pyramidal inversion. Pyramidal inversion. Or we can say umbrella effect. Umbrella effect. You know what happens? At room temperature, the inversion of one enantiomeric form into another is so rapid that it is very difficult to isolate those enantiomeric forms, and hence it is optically inactive. So, suppose if I have something of this sort, yes? Suppose this is R1, this is R2, this is R3. So the hybridization here is sp3. And obviously its enantiomeric form, non-superimposable mirror image will be something of this sort. Yes or no? Let us say this is R1, R2 and R3. So these are your enantiomeric forms. But you know, one enantiomeric form goes into the other. I mean, it forms, suppose this is A and this is B. So A, while going to B, proceeds via a transition state which is planar. A planar transition state. So it goes via planar transition state. When I say planar transition state, that means I have something like this. R1, R2 and R3. And you know what? Now the hybridization is sp2 because it is planar. Yes or no? Tell me.
Yes.
So this conversion is so rapid at room temperature that it is very difficult to isolate these enantiomeric forms, and hence this amine is optically inactive. In spite of being chiral. So please, this is important to note.
This is the acid phosphorus normally.
Yes. So you just pass that plane and see if they are superimposable or not superimposable. So that is what I'm saying. Try it and then tell me. Okay? Is that clear?
Yes.
Tell me if this is clear. So please remember that instead of being chiral, they are non-superimposable. In spite of being chiral, they are optically inactive. Now, if you remember, we discussed isomerism. I told you there are different types of structural isomerism, like position isomerism or metamers, functional isomers. So suppose if I give you isomerism, let us discuss the isomerism in amines. Let us discuss the isomerism in amines. C2H7N. Okay, what is this? C2H7N. Tell me. Can I say one of the structure possible is CH3, CH2, NH2? Yes or no?
Yes.
Ethanamide? Tell me yes or no?
Yes.
And one of the structure possible is this CH3, NH, CH3. Yes or no? This is your 1 degree amide and this is your 2 degree amide. And both of them, which type of isomers are these? Metamers. They are metamers. They are metamers. I hope this is clear.
Yes.
They are metamers, depending upon the carbon atoms on both the sides of the atom. Now suppose if I have C4H11N, please tell me what first butanamide, CH3, CH2, 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 NH2. What structure is this?
Yes.
Yes or no? Yes. Another structure can be this CH3 and CH3 and CH2 CH3. Is it possible? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 hydrogens. Yes or no?
Yes.
Tell me. Another structure is this CH3, CH2, NH, CH2, CH3. Any problem? This is also possible. And what about this? CH3, NH, CH2, CH2, CH3. Yes or no?
Yes.
So what is this? Which amine is this? 1 degree. What about this? 3 degree. What about this? And what about this? 2 degree. And can I say all of them are metamers? They are metamers. Yes or no? They are also your metamers. They are also your metamers. Tell me if this point is clear.
Yes.
Yes, tell me if this point is clear.
Yes, sir.
Okay. Next. So, when I say amine, see, RNH2. Can I say amines are polar in nature, just like alcohols? Yes? Amines are polar in nature?
Yes.
Amines are polar in nature. And why is it so? Because of the electronegative end? Yes or no? Okay. Because of the electronegative end. Electronegative nitrogen. And if they are polar, so suppose if I write it like this, okay, what will happen? Tell me. What will happen? Or let me write this in the other way. Suppose if I write it like this, R, N, H, let us say 1H. I'm showing it like this. Now what will happen? Can I say it undergo intermolecular hydrogen bonding?
Yes.
Yes or no? Can I say it can undergo intermolecular hydrogen bonding? Tell me. Yes or no? Because there is lone pair of electrons. Yes? Tell me if this is clear. Tell me if this is clear.
Yes.
Can I say it is capable of undergoing intermolecular hydrogen bonding? Okay. Now we also discussed about such type of bonding in alcohols. If you remember that alcohols also undergo intermolecular. So when I compare it with the intermolecular hydrogen bonding in alcohols, can I say this is weaker? Can I say this is weaker than alcohols? Yes or no? Can I say this is weaker than alcohols? Why? Because alcohols are more polar than amines. Yes, they are polar, but they are less polar than alcohols. Yes or no?
Yes.
Than alcohols. So can I say their boiling points are lesser compared to the alcohols of comparable masses and also to carboxylic acids of comparable masses? Yes or no? So boiling points are lesser compared to alcohols and carboxylic acids of comparable masses. Yes? Of comparable masses. Any problem? Tell me किसका ज्यादा होगा? Yes, because they form diamond. Yes or no? Okay. Carboxylic acids. Is that okay? So boiling points are lesser compared to alcohols and carboxylic acids of comparable masses. Now, but suppose if I have 1 degree amine and I have 2 degree amine and I have 3 degree amine, can you arrange it in the order of boiling point? Okay. Tell me. Can you compare or arrange it in the order of boiling points? 1 degree more. And you are saying 3 degree should be more? Tell me. Yes, those who are present online, please tell me. I'm not talking about the basicity. It is boiling point. Yes, those who are present online, please tell me.
So 1 becomes more boiling point.
Okay. So 1 degree is having more boiling point than 2 degree and then 3 degree. Why? Because in 1 degree we have 2 hydrogens and they can undergo more. That more the number of hydrogen atoms attached to nitrogen, more will be the hydrogen intermolecular hydrogen bonding possible, and hence more will be the boiling point. Here, no such intermolecular hydrogen bonding is possible. Yes or no?
Yes, sir.
Is that clear to everyone?
Yes.
Yes, sir.
And for the same reason of intermolecular forming this intermolecular hydrogen bonding, lower members of amines are soluble in water because they can undergo intermolecular hydrogen bonding with water molecules. But yes, as the size of this alkyl group increases, the non-polar part is increasing. So you know that is hydrophobic. So and the solubility keeps on increasing, right? But the lower members are soluble. The lower amines are soluble. Amines are soluble in water, and the reason is same. That is intermolecular hydrogen bonding. For example, ethanamine. Let me discuss ethanamine. Suppose if I have CH3, CH2, NH2. Yes or no? I have NH2. So let me show NH2 like this. It can undergo intermolecular hydrogen bonding with water.
Yes.
Yes. Similarly, this. Yes or no?
Yes.
Similarly, this can undergo hydrogen bonding, 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 and so on and so on. Is that okay?
Yes.
Is that clear to everyone?
Yes.
Yes,
Yes,
sir.
sir. Yes.
Yes, sir. All right. Tell me.
Yes.
Is that okay? The lower members are soluble in water. Why? Because of the intermolecular hydrogen. Is that clear?
Yes.
Next, methods of preparation. Methods of preparation. The first method is ammonolysis. The first method is ammonolysis, that is reaction of alkyl halides with ammonolysis. Reaction of RX with ammonia. Is that okay? Now look here. I have RX and I'm treating it with, or we can write it like this. I have ammonia. Okay? I'm treating it with RX. So minus HX, and what will we get? RNH2. Any problem? Then suppose if I have RX in excess, then we will have R2NH.
Yes.
And since I have RX in excess, so till the time I have these hydrogens, I will get the amides, right? So this is the 1 degree, this is the 2 degree, this is the 3. Now suppose, so can I say that suppose if I have ammonia in excess, then in that case 1 degree amine is the major. Yes, 1 degree amine being the major. But suppose if I have RX in excess,
3 degree.
3 degree amine is the major. 3 degree is the major. Is that clear?
Yes, sir.
Tell me if this is clear.
Yes, sir.
Yes, sir.
Clear?
Yes.
Next. The second method, reaction of, the first one was reaction of RX with ammonia. This is reaction of alcohol with ammonia. So look here, ammonia reacting with alcohol, let us say I am reacting it with RCH2OH. So minus H2O,
Yes, sir.
what do I have is RCH2 NH2. Then again, if I have more alcohol, then RCH2 NH RCH2. Yes or no?
Yes, sir.
And suppose if I have more of alcohol, then RCH2 RCH2 RCH2. Is any problem?
No, sir.
But if you see, in both of these methods, I am getting a mixture of 1 degree, 2 degree, and 3 degree amines. Yes or no?
Yes.
1 degree, 2 degree, and 3 degree amines. So what I'll do is I'll distinguish among these 3 types of amines. Since I'm getting 3 types of amines, what I'll do is we'll have a distinguished test to distinguish among 1 degree, 2 degree, and 3 degree amines. Okay.
Yes.
Now, so basically what we are doing is we are separating 1 degree, 2 degree, and 3 degree amines. Okay. Now, this reaction is basically done in the presence of Al2 O2, O3, or you can use sodium oxide, right? At temperature 360 degrees Celsius. Now, look at. So separation of 1 degree, 2 degree and 3 degree amines. Since we got the mixture, the separation of 1 degree, 2 degree and 3 degree amines. Now, so we are using Hinsberg test. We are performing this test to distinguish. Yes, and also to separate. Now, how will I distinguish among these three? So, suppose if I have primary amine, is that okay? It is treated with Hinsberg reagent, that is benzene sulfonyl chloride. So, it is treated with Hinsberg reagent. This is your Hinsberg reagent, benzene sulfonyl chloride. Is that clear?
Yes, sir.
This is your benzene sulfonyl chloride. Is that clear?
Yes, sir.
Okay. Now, so this is your Hinsberg reagent. What will happen? Minus HCl. What do I get is R, NH, yes. Yes or no?
Yes,
What is the name of this? Yes, what is the name of this? This is alkyl benzene sulfonamide. N-alkyl benzene sulfonamide. Yes or no?
yes,
Now, when it is treated with aqueous KOH, we get a water-soluble salt, water-soluble potassium salt of sulfonamide. We get a water-soluble potassium salt of sulfonamide. Potassium salt of sulfonamide. Is that clear?
yes, sir.
Like this. Is that clear?
Yes, sir.
Now, when I treat this Hinsberg reagent with 2 degree amine, R2NH plus Hinsberg reagent, what do I get? I get something of this sort. N-dialkyl benzene sulfonamide,
Yes, sir.
N-dialkyl benzene sulfonamide. Yes or no?
Yes, sir.
And then when I treat it with aqueous KOH, there is your precipitate that is formed. That means water insoluble precipitate. Water insoluble substance is formed. Yes or no?
Yes, sir.
Insoluble salt also exists, which is in the form of precipitate. And when you have 3 degree amine and you react it with Hinsberg reagent, there is no reaction. There is. Tell me if this point is clear.
Yes, sir.
Tell me if this is clear.
Yes.
Yes, tell me if this point is clear.
Yes.
Is that clear to everyone?
Yes, sir.
Yes, sir.
Is that clear to everyone? Okay. Please note it down. Now the next part is important. So in these two methods, we were getting a mixture of amines. Now we are doing exclusively for 1 degree, 2 degree and 3 degree amines. So the first one is the methods of preparation. They are the methods of preparation exclusively for primary amines. Alright, we will get primary amines from. Number 1. Reduction. This part is very important. Reduction. Reduction of first nitro compounds. Nitro. Nitro. So look here. Suppose if I have RNO2 and I want to convert it into RNH2, then the reagents used can be hydrogen in the presence of palladium or nickel, hydrogenation, reducing agent, or zinc in the presence of HCl, or Sn in the presence of HCl, or iron in the presence of HCl, yes or no? Or we can use lithium aluminium hydride, lithium aluminium hydride. Any of these reducing agents we can stimulate the system.
Yes.
Is that clear? Now it's mentioned that this is usually preferred. This is usually preferred because FeCl2 form gets hydrolyzed to HCl. Gets hydrolyzed to form HCl. So we don't require large amount of HCl to initiate the reaction because we are getting nice. Right? So they say that this is usually preferred. Is that clear?
Yes.
Next is your reduction of nitriles. Reduction of nitriles. How do we get nitriles? Very simple. Suppose if I have RX, I treat it with KCl. So I get RCl. Yes or no?
Yes.
Now, this can be reduced in the presence of hydrogenation. So basically, I need a reducing agent here as well. So hydrogen, let's say in the presence of nickel, or we can use sodium amalgam in the presence of ethanol, or we can use LiAlH4 in order to get amine. In order to get 1 degree. Tell me if this is clear.
Yes.
Is that clear? Third, the reduction of amides. The reduction of acid amides. Look here. RCONH2 and I want to form RCH2NH2. Here. So I can use lithium aluminium hydride followed by hydrolysis to form this. Yeah, so that is in the presence of lithium aluminium hydride. Tell me. Yes or no? Yes? Shall I? Okay? Alright. Please note it down. Yes, sir. Is that clear to everyone?
Yes.
Okay.
Yes.
All. Next. So what is reduction? Addition of hydrogen. So you can easily understand it, I hope.
Yes.
Yes? Break this bond, give H to this, H to this, H to this, H to this. Get RCH. Alright, look at it. Next is your reduction of oximes. How do we get oximes? Oximes are the reaction of ammonia derivatives with carbonyl compounds. Which ammonia derivative? Hydroxylamine, right? So we are, suppose if I have this and I treat it with hydroxylamine, I get what do I get? Elimination of water. This is addition elimination type reaction, remember?
Yes.
So what do I get? Oxime and then reduction of oxime in the presence of LiAlH4, you get amine. Is that clear to everyone?
Yes, sir.
Again, one thing here. Alright? Next. Aldehydes and ketones. This is important. Aldehydes and ketones. Now, basically, ammonolysis. So see, you know that when we react with ammonia, what do we get? Imine. Remember? Suppose if I have this and I treat it with ammonia, what do I get? Imine. This is imine, yes?
Yes.
And then the reduction of imine will give you amine. So see, what reagent you can use? So hydrogen in the presence of platinum you can use, or there is a specific reagent, please remember this, that is sodium borohydride, cyanoborohydride. Okay, cyanoborohydride. So this is your NaBH3CN, cyanoborohydride. Please remember this reagent. And what do I get? So reduction of imine to amine. Reduction of imine to amine. Is that clear? Reduction of imine to amine. Okay?
Yes, sir.
Yeah. Why? Just okay. Sorry. So you also want tea?
Yes.
Okay. So you want tea. So why don't you bring your own tea? Iced tea, normal tea, ginger tea, lemon tea, and also give it to me. Or maybe some chocolate truffle things, some coffee, caramel, hazelnut, and also give it to me in the glass. Instead of doing that, you are asking me to lower down the temperature of this thing. Sorry. Next is your. So first one was reduction. Second is hydrolysis. Second is hydrolysis.
Yes.
See, this is important. There is one thing important that is very important to know. That reduction of nitriles, but hydrolysis of isonitriles. Hydrolysis of isonitriles. Hydrolysis of isonitriles. Okay. So, isonitriles, when it is hydrolyzed in the presence of, let's say, acidic hydrolysis. So, what do you get? You get RNH. Is that okay? We also get acid plus we get COH or we don't know, we get HCOH basically. Yes? So let me write. Is that clear to everyone?
Yes.
Yes.
Okay. And also the hydrolysis of alkane isocyanates, although we will discuss this in Hoffman-Bromide reaction also. Alkane isocyanate. Alkane isocyanate. For example, I have R, N, double bond C, double bond. This is your isocyanate, alkyl isocyanate. And hydrolysis of it will give you RNH2. Yes or no?
Yes, sir.
Let us say alkaline hydrolysis in the presence of KOH, and what else you get is K2CO3. Tell me this is clear.
Yes, sir.
Yes? Tell me this is clear. If you want to balance it, K2, 2. Is that okay?
Yes.
Is that clear to everyone?
Yes, sir.
Yes, sir.
Next reaction is very, very important. Star mark this reaction. Hoffman-bromamide reaction. Hoffman-bromamide reaction or degradation reaction. Is that okay?
Yes.
Now look here. Suppose if I have bromine plus NaOH, can I also write it NaOBr? Yes. Sodium hypobromide. Yes. Okay. Look here. So what happens? Suppose if I have amide like this. Is that okay? Reacting it with bromine in the presence of strong bases like KOH or NaOH. Can use NaOH. Yes?
Yes.
What do you get? RNH2, that is amine with one carbon less than in the parent amine. Yes? Amine with one carbon less than the parent amine. Plus, we get KBr. Plus, we get K2CO3. Plus, we get water. This is the complete reaction. Is that clear?
Yes.
Tell me. Is that clear? If
Yes.
you want to balance it, you can write 4 over here. And 1, 2, 2, 3. Everything is balanced. Tell me if this point is clear.
Yes.
But what is more important is the mechanism of this reaction. There is a formation of an intermediate. So what is that intermediate? Although we have already discussed that intermediate, that is alkyl isocyanates. So it proceeds via, let me write, it proceeds via isocyanate intermediate. Isocyanate intermediate. Is that okay? Isocyanate intermediate. Quickly do it, then we discuss the mechanism. Shall we discuss the mechanism?
Yes.
Okay. Look here. Suppose if I have R, C double bond O, H. Okay. In the first step, what will happen? I have Br2. Okay. This bond is polar. So what do I get is this. Okay. This is the first step. Tell me this is clear.
Yes.
This is N-bromoamide. N-bromoamide. What will happen in the next step? Please remember the second H is not replaced by bromine. Okay, the second H is not replaced by bromine. What will happen? This H, you have a base.
Yes.
So base will abstract this particular H and these electrons goes to nitrogen. Is that clear? So what will happen? R, C double bond O, and this is your N negative. Yeah. Is that clear?
Yes.
Is that clear? Now what will happen in the next step? This Br leaves in the form of Br minus. Okay? In the form of Br minus. So what do I have? R, C double bond O, N. This is a lone pair of electrons. Yes? This is your acyl nitride. This is your acyl nitride. वैसे तो you can also acyl nitride. वैसे तो you can also understand it this manner that when this Br leaves, what happens? This R migrates to this N at the same time. Okay. So what will happen? See, C double bond O. Is that clear?
Yes.
And this bond goes here. Double bond N and R. This is your alkyl isocyanate. That way. Yes, so this is your alkyl isocyanate. Alkyl isocyanate. Tell me if this is clear. So basically there is 1,2 migration of this alkyl group. 1,2 migration of alkyl. Any problem? 1,2 migration of this alkyl group. Tell me if this is clear.
Yes.
Is that clear to everyone?
Yes, sir.
Yes.
Okay. Now hydrolysis of this will give you the amine. Yes? Okay, so let us discuss. This is R, N, double bond C, double bond O. Hydrolysis of this will give you amine. So see, in the first step, what will happen? So you have H positive, OH minus. What we can do, we can break this down. Right? So we can write, we know that here we will have partial positive. So what we can have is R and H. Okay? We can have R and H. And this is C double bond O, OH. So OH with this and H with this. This is your carbamic acid. Carbamic acid. In the last step, decarboxylation. And you will get RH2. Simple. Is that okay? You will get RH2. Tell me if this point is clear.
Yes.
Yes? Tell me if this point is clear.
Yes.
Yes.
Is that clear to everyone?
Yes, sir.
Okay. So this is one of the reactions which proceeds via isocyanate intermediate. But there are other reactions also which proceeds via isocyanate intermediate and it gives you 1 degree. Okay. Like for example, other reactions. They also proceeds via isocyanate intermediate. Is that clear?
Yes.
The first one is R C double bond O NH-OH. Suppose if you start with this and you treat it with acetic anhydride, okay, followed by hydrolysis. So see, acetic anhydride, you will get alkyl isocyanate, followed by hydrolysis of alkyl cyanate, you will get amine. Which amine? 1 degree. 1 degree. Please remember. Now suppose if you have something of this sort, RC double bond O N3. This is your azide, acid azide. N3 is azide, acid azide. When you heat it, you get isocyanate intermediate, then hydrolysis of that will give you amine. Is that clear?
Yes,
Give you
sir.
amine. Tell me if this is clear? Clear?
Yes, sir.
Just a second. And suppose if you have acid like RCOOH and when you treat it with HN3, is this ammonia?
Right.
This is hydrozoic acid. This is hydrozoic acid, not ammonia. Please remember, this is not ammonia. Hydrozoic acid. In the presence of concentrated H2SO4, we get RH. Is that okay? So all these reactions proceeds via isocyanate intermediate in order to give you amine. This is your Lawson rearrangement. Lawson rearrangement, where we start the reaction from hydroxamic acid. Hydroxamic acid. Oxamic acid. Is that okay?
Yes.
Hydroxamic acid. Okay.
Yes.
And the next, the decomposition of acid azide followed by hydrolysis is your Curtius reaction. Curtius reaction. And the reaction of acid with hydrozoic acid in the presence of concentrated H2SO4 is your Schmidt reaction. Can I? Is your Schmidt reaction. Tell me if this is clear. This is just Schmidt reaction. Curtis. Lawson, Curtis, Schmidt, and Hoffman bromide all proceed via isocyanate intermediate in order to give you amine. Tell me if this point is clear, those who are present online.
Yes, sir. Yes, sir.
Tell me if this is clear.
Yes, sir.
Is that clear to everyone?
Yes.
Tell me if this is clear. Done.
Yes, sir.
Next reaction. This was reaction number 3. Let us discuss the next reaction. That is also very important. Star market. Gabriel Thalamide synthesis. I hope you have noted that all of these methods are exclusively for primary amines. Gabriel Thalamide synthesis. Alright?
Yes.
Is that clear? Now we start. If you remember in the last class when we were discussing carboxylic acid, dicarboxylic acid, so I told you that suppose if I start with phthalic acid, right? So let us discuss the preparation of thalamide. So this is the phthalic acid. This is a phthalic acid.
Yes.
Yes or no? Suppose if I perform the ammonolysis of it, okay, what do I get? I get something of this sort. COO minus NH4 plus COO minus NH4. Then when I heat it, there will be removal of 2 molecules of water, and what do I get is this? CO NH2 CO NH2. Tell me if this is clear.
Yes, sir.
CONH2 CONH2. Now, when I heat it further, there is a removal of ammonia. Yes, and what do I get is this. Yes or no?
Yes, sir.
Yes or no? So, this is a phthalic acid. This is a phthalic acid. Yes or no?
Yes, sir.
Phthalic acid. This is your ammonium phthalate. Ammonium phthalate. This is thalamide. Thalamide. And this is the reactant that we require, thalamide. This is your thalamide. Is that okay? So this is Gabriel Thalamide synthesis. Clear?
Yes.
Now let us discuss the reaction. So when we treat this thalamide, with a base, like KOH, what will happen? This will be abstracted. Yes? And what do I get is potassium salt of thalamide. What do I get is potassium salt of thalamide. This is the potassium salt of thalamide. Is that clear?
Yes, sir.
Now, when I treat it with primary alkyl halide, please remember First of all, it is primary aliphatic amide. Primary aliphatic amide. There will be SN2 reaction. Yes or no? Please remember primary aliphatic amine only, not aryl amines. Because aryl amines do not give such reactions SN1, SN2. We discussed the reactions, addition, elimination, and elimination, addition reactions there. Elimination, addition, where we discussed the where the reaction proceeds via benzene intermediate as in Dow's process. Right? So please remember, this is your aliphatic amine, primary aliphatic amine. Is that clear?
Yes.
So what do we get? NR? Yes or no? This is your N-alkyl phthalimide. N-alkyl phthalimide. Yes or no?
Yes.
N-alkyl phthalimide. Yes or no? Now, the hydrolysis of this. Now, the hydrolysis of this. What will you get? Here we will get phthalic acid plus we will get RNH. Is that okay?
Yes.
Now basically what happens, look here. Actually we can show it like this. Although that is also correct, we can show it like this. Let's suppose if I perform the acidic hydrolysis, okay? Then what do I have is phthalic acid, okay? And look here, and obviously I will have RNH3 positive, that's ammonium salt. Okay. Now what will happen? We have a base. Yes, we have a base. So it will be RNH2 plus H2, simple. The purpose is that we are getting primary, and we are getting one layer, primary, aliphatic amine. Can we get aromatic amine? No, because we cannot have the aromatic halide. So aromatic amine cannot be prepared. Please remember. So aniline cannot be prepared. Aniline cannot be prepared. Yes or no?
Yes.
By this method. But yes, aniline can be prepared via. If I ask you, can aniline be prepared? Yes, aniline can be prepared. Why? Why? Because aniline is also 1 degree amine, but that is aromatic 1 degree. That is also 1 degree, yes or no? It is aromatic 1 degree amine. So it aromatic 1 degree amine. But Gabriel phthalimide synthesis is for aliphatic 1 degree. Is that clear?
Yes.
Is that clear to everyone? Those who are present online? This like.
Yes, sir.
Is that clear to everyone?
Yes.
Yes, sir.
Yes. Please note it down. Please note it down. Please note it down. Yes or no?
Yes.
Tell me this is clear? Clear? Okay. So let us discuss one question. We discussed the ammonolysis of alkyl halide. Remember?
Yes, sir.
Alright. So basically it is having a disadvantage. Why? Because we are getting a mixture of products. Yes or no?
Yes, sir.
We are getting a mixture of products. That is 1 degree, 2 degree and 3 degree. So this is the disadvantage and limitation of ammonolysis. So in order to address it, what we can do is we can take ammonia in excess so that we can have 1 degree amine as a major. Is that clear?
Yes.
This way. Alright. Now suppose if I ask you, can you arrange the reactivity order of Rx here? Suppose you have Ri, Rbr, RCl. Tell me which one is more reactive. Tell me which one is more reactive. Ri? Ri? And Rbr? Then answer yes, because we require the splitting of Rx bond. So weaken the bond, and you also know that the nucleophilicity of I negative is more. So it's a better leaving.
Yes.
Yes? So the reactivity of Ri is more than RCl is more than Rb. Is that clear to everyone?
Yes, sir.
Tell me, is that clear
Yes.
to everyone? Alright. Alright. Next question. Next question. Just a second. Alright. Next question. IUPAC name, IUPAC nomenclature of the amide IUPAC nomenclature of the amide which gives propanamide by Hoffman degradation method. Hoffman's bromamide reaction. Hoffman's bromamide reaction. Do it. Tell me. What is the name of such amide? I'm waiting. What is the name? Butanamide. Butanamide, simple. Butanamide is the IUPAC name. Propanamide you are getting, so obviously it will be one less than the parent amide. One carbon less than the parent amide, and parent amide will be butanamide. Is that clear? So let us discuss the methods of preparation exclusively for secondary amides. Exclusively for secondary amides. Exclusively for secondary amides. The first one is reduction. Again we are getting reduction. But this time reduction of what? Reduction of isonitriles. Reduction of isonitriles. There it was nitriles. Reduction of isonitriles. So suppose if you have R and C and I want the reduction of this in order to get RNH. Look here. RNHCH3. What you can use? Hydrogen in the presence of platinum, or you can use LiGH4. Is that clear?
Yes.
platinum, or you can also use nickel. Tell me if this is clear.
Yes, sir.
Is that clear to everyone?
Yes, sir. Yes, sir.
If you remember, in the primary amide, when we were discussing the reduction of amides into primary amides. So look here. So basically, if you remember, recall it. So basically, if I have this type of amide, it's a no. And I perform the reduction of this, so I got 1 degree amide, if you remember.
Yes, sir.
But suppose if I have this kind of amide, so can I say I will get RNHCH3 kind of amide? Amine. 2 degree. Tell me yes or no? Yes or no?
Yes, sir.
RCH2 because RCH2. Here you are getting Here we are getting RCH2. RCH2NH2. So here we will get RCH2NH. This kind of amine. 2 degree amine. So here we were getting 1 degree amine, here we are getting 2 degree amine. So can I say by reduction of substituted amines? Substituted amines. Yes or no?
Yes, sir.
Yes, sir.
Like for example, if you have RCONH, let's say R dash, and you are performing the reduction of this. What do you get? RCH2NH R dash. 2 degree amine. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
Tell me.
Yes, sir.
I hope this is clear.
Yes.
Yes, sir.
Okay. Next, exclusively for tertiary amines. Exclusively for tertiary amines. Exclusively for tertiary amines. Okay. Reduction again. But this time it was the mono-substituted amide. Can I say di-substituted amide? Yes, di-substituted amide. Di-substituted amide. Like RCON R double dash R. Is correct. Yes. So again, hydrolysis of it, reduction of this will give you RCH2 and R dash R double dash. We are getting 3 degrees. Tell me if this point is clear.
Yes, sir.
Tell me if this is clear.
Yes, sir.
Yeah.
Yes.
Next is also important. One, basically in alkenes, while discussing alkenes, we didn't discuss this Hoffman elimination basically. Self elimination we already discussed, but this is your Hoffman elimination. Okay, this is your Hoffman elimination. Look. And where we discuss Hoffman elimination is when we heat quaternary ammonium salt. When we heat quaternary ammonium salt. Quaternary heating for tertiary. Heating quaternary ammonium hydroxide. The ammonium salt. Okay. Look here. What we want. This is important. Look here. Suppose if I go CS3 and CS3, CH3, and here goes CH2, CH3, positive, OH minus. This is a quaternary ammonium hydroxide. Yes or no?
Yes.
Yes or no? Now when you heat it, you know what happens? Look here. This is the alpha hydrogen. Elimination means alkene formation. This is the alpha. This is the beta. So just break this bond. You will get tertiary amine, CH3, N, CH3, CH3, plus this is beta. This will come over here. This will be alkene formation. Plus you will get water. Is abstract करेगा this H. Is that clear?
Yes, sir.
Tell me this is clear.
Yes. Yes, sir.
Yes, sir.
Is that clear to everyone?
Yes.
If this is clear, let me give you one question. Suppose if I have this,
Yes, sir.
please do it. Shall I?
Yes, sir.
Okay, look at it. Suppose if I have this CH3, CH2, and CH3, CH2, CH2, CH3. Clear? And you are having CH3 over here and positive and OH minus. And when you heat it, can you please tell me the products? And obviously you will get a tertiary amine, that's for sure. Tertiary amine is fine. But I just want to know about the alkene. There are two types of alkenes formed now. Yes or no? Because there are two types of beta. Can you please tell? Because alpha beta. Beta. So there will be two alkenes. CH2 double bond CH2 plus CH3 CH double bond CH2. So you are saying this is the major product. This is your more substituted, and this is your less substituted. Now what is Hoffman alkene, which is less substituted? So less substituted is the major product. This is what Hoffman elimination is. I hope this is clear. Tell me this is clear. So 3 degree definitely you will get. 3 degree amine definitely you will get. But I just want to know about the alkenes. Tell me this point is clear. Yes. Yes, tell me this point. Just give me 1 minute. So this is the nitrogen containing compounds 1. So I am writing. Tell me this point is clear.
Yes.
Is it clear to everyone, those who are present online?
Yes, sir.
Yes, is it clear to everyone, those who are present online?
Yes, sir.
So any problems to whatever we have discussed today? To anyone? Those who are present online as well as offline?
No, sir.
No? Yes, tell me. Any problem? Great. What did I ask? What did I ask? Any problem to whatever we have discussed in the class today? But it's not exclusively for you. Tell me. Adiba, Jyoti, Jyotsna, Ganeshka, Keswan, Prerna, Varshita, Shazlina,
Noida, sir.
Ronik.
No problem, sir.
So please keep revising the notes. In the next class, we'll continue with this. So we'll start with the chemical properties of amines, where we discuss the very important characteristic, that is basicity of amines, and we will also discuss the aromatic amines. We will have this. There is one important reaction which is carbylamine reaction. We'll discuss that, and we'll talk about the diazotization reaction. Right? Although we have discussed it previously as well, but we'll talk about diazotization reaction, the formation, the azocoupling reaction, also the electrophilic substitution reactions of aniline. Right? So these are the things that we'll discuss. Is that okay?
Yes.
Okay, then thank you so very much. Do take care. We'll continue from here in the next class. Thank you so much. Do take care.
Thank you, sir.
Thank you, Krishna, for organizing.